But today, even though we did this a little bit yesterday and it was more in our calculator, we're going to talk about graphing polynomials and some of the things that we're going to be looking for, or some of the things that we need to do when we graph those polynomials. And some of it will be kind of similar to what we did yesterday. Some of it will be a little bit different process. We can definitely use our calculator to help us and kind of guide us with what the graph's going to look like, very much like what we've done with other graphs throughout the semester so far. What I will tell you is that all these polynomials are going to look a little bit different depending on what degree they are, depending on what type of polynomial they are. Each one's going to look a little bit different. You're going to kind of start to figure out, like based on the degree, kind of what it's going to look like, but each one's still going to look slightly different. All right, so first up, we're going to say P of x is a polynomial of degree n. Okay? And I'm not giving you a polynomial right here because we're going to talk about some important information that we're going to use as we start to graph today. So for any polynomial, there's certain information that we will always know based on the degree of that polynomial. And the degree, once again, is the highest exponent of that polynomial. That's how we name it. Like yesterday we talked about if it's cubic or quartic or quintic or whatever it is, it's always based off of the highest exponent of that polynomial. And we call that the degree of the polynomial. Okay, so there are three pieces of information that we're going to talk about based on the degree. The first one it will have at most n real zeros. So what that means is if my degree is 3, let's say, then I could have 3 would be the most real zeros I could have. I can't have more than that, right? And we kind of talked about that a little bit yesterday. Like if I have a quadratic, I can go back to even last chapter and say if I have a quadratic, it could cross the x-axis 2 times, right? But it's not guaranteed to cross the x-axis 2 times because we saw ones that would come down and hit the x-axis and go back up. We saw some that never touched the x-axis at all. So when we talk about n real zeros, that means that's the number of real solutions I could have, and that's the most. Another one that kind of goes along with that, at most n x-intercepts. We talked about this a little bit yesterday too. If I have a cubic polynomial, once again, of degree 3, then it can cross the x-axis 3 times at the most. If I have a degree of 4, it could cross the x-axis 4 times. It's not guaranteed to cross it 4 times. That's why we use the words at most. 4 is the most it could cross if it's quartic. Same as a quadratic, right? We talked on a quadratic that if it's a degree of 2, it could cross the x-axis twice, but doesn't have to cross it twice. And we saw some examples of that in the last chapter. And then the third piece of information that we can tell from the degree is that it has n minus 1 turning points. So it's always going to be 1 less than the degree. So if I have a degree of 3, that means it would have 2 turning points. If I have a degree of 2, you think about it like a parabola for a quadratic equation, then it's only going to have 1 turning point. And that's where like it has a minimum maximum. And that's where the graph changes direction, basically. We call that a turning point of a graph. So if I were to look at like a cubic polynomial, just to kind of show you some examples of what's going on here. A cubic polynomial is typically going to take on the shape of something like that. I call it the snake-like graph because it's kind of like what it looks like. And because it's cubic, which means my highest exponent is x cubed, right? Then it could cross the x-axis up to 3 times, and sure enough, we look at it, that's what it does, okay? It cannot cross more than that. It has 3 x-intercepts. We would also say those are real zeros because if it has 3 x-intercepts, then those zeros are also real, okay? And so here we would say this one has 3 real zeros, 3 x-intercepts, and it has 2 turning points. And the 2 turning points are where this graph is going to change direction. So it would be kind of like what we did yesterday where we found the maximum and the minimum. Those are what we call turning points because it goes a different direction. Hey, Mr. Mueller.
Just the best and the brightest today, huh?
Yep. Everybody else is out.
I have 1 student this hour.
1. Yeah.
At least you got more than that.
A few more. Yeah. That's what I had last hour too, was 1 student.
1?
Yeah. Yeah.
It's a little awkward to teach 1 student.
Yeah, probably so. Yeah. Some good interaction though, right?
Right. So
Yeah.
you got my undivided attention. If you got questions,
Yeah.
I'll give you time
Yeah.
to ask.
What you got going on?
Can I interrupt you for just like,
Yeah.
since I already have? Okay, so 7 versus 2. I think we can move my assignments from another class.
okay. Yeah, yeah. So
Oh crap, I can't count. It's 9.
Let me pick on one of these classes.
Is it your birthday, Albany?
Yeah. Report.
So I'm wearing this shirt.
Reporting system.
Did your parents make it for you?
No.
Who did?
Nope.
Doesn't have a shirt.
That's right.
No.
Import from.
Well, it can't be CAG squared, actually.
What's K squared?
No, it's not.
No, I don't know right either. So maybe the first one was right.
Well, what do you think CAG means?
I have no clue. He said something about
Yeah,
New
so
Jersey.
select.
Yeah, that's the main color. That's good.
Copy a Cambridge course. Okay, and then
I think you're on the positive. What?
is this, is this, what is this one? What is it say?
City line.
That you're importing to.
I ain't going to Ryan. You're very bad quick.
Oh, yeah. So that's one you're copying, so if you want to build that
Did you
one,
find where you live?
spring of last year.
Show me the English.
Well, I can tell you the name of it. CAG Street. Actually, it's actually.
I just usually do all comes together.
What, ask me?
I don't know, it's a good question. I don't know if I've done just specific ones. Oh, and then here, you select country that you want to.
There you go.
And now it's in use, and that's all done, it should be there.
Thank you.
Yeah.
Sorry.
It's all right.
Sorry.
Okay, so if I gave you another one here, one very, very similar. It's still cubic, right? Still has the same basic shape. But this one's a little bit different. Still a cubic polynomial. Still looks pretty much the same. And so what we're going to say on this one is this one only has 1 real zero, 1 x-intercept, still has 2 turning points. Okay, so if it only has one real zero, then what do you think that means about my other zeros? Because if it's cubic, that means I got to account for 3 zeros in some shape or form. They're imaginary, yep. And so we would have to somehow find, and that's something we'll do later in the chapter, somehow find what those other zeros are going to be and how we would go about doing that. Okay. One other possibility here, just so you can kind of see some different things, is if I, once again, do this. Yesterday we talked about there being a bouncer where it comes down, hits the x-axis, and comes back up. So on this one, we would say this one has 2 real zeros. 2 x-intercepts, and still has 2 turning points. Okay, and once again, to go back to yesterday, if I look at this, then we call this a double root. Okay, whenever it bounces here, we said that has a multiplicity of 2. So whenever it bounces off the x-axis like this, and once again, that's just the word that I use. I say that it bounces off here. We count this as 2 zeros. And so typically it'll be like a double root, like x minus 3 squared. X minus 3 and x minus 3. We count that as 2 zeros. Okay, it's the same 0, but it happens twice. And so it really only touches the x-axis in 2 different places, but because it comes down and hits at that point, we count that for 2. And so that would account for our 3 zeros. Because this is a multiplicity of 2 right here, this would count for 2 zeros, this is 1, and that gives us our total of 3. Okay, so 3 different scenarios, all based off the same basic type of graph because it's cubic, but different kinds of things are going to happen there, where we're going to have different kinds of solutions and different kinds of things. The good thing today is we're not necessarily going to find our zeros in every situation. We're going to find them if we can, but if they're imaginary, we're not going to worry about that today. We're going to find its real zeros if we can find those and use that as part of our graph, but we're just trying to develop what the graph's going to look like based on some information that we know. Okay? All right, so when we graph, I'm going to kind of go through some steps here. One of the first things that we're going to do is what we call the leading term test. We talked about that yesterday. I told you that I'm just going to call it LTT for right now. And what that tells us is the end behavior of the graph. Okay? And so we don't necessarily know a lot of information about it other than, is it going to start up and end up, or is it going to start up and end down? What kind of end behavior is that graph going to have? And I can tell that just by looking at it from the very beginning of what type of end behavior that graph might have. Okay, another piece of information is we're going to look for the zeros of the function. And for today, we're not going to be able to find the imaginary zeros. Okay, we're not going to worry about that today necessarily. Eventually, throughout this chapter, we will find what those imaginary zeros are and how we can get there. But today, really, we're just going to be looking for the real zeros. Another key piece of information is the y-intercept. And in order to find the y-intercept, we simply just plug 0 in for x into the function. Okay, and I didn't really say it here, but the zeros are going to go right along with the x-intercept. So even though I didn't say we're going to find the x-intercepts, that's what we're really doing when we find the zeros. We're finding the x-intercepts of that graph. We're also finding the y-intercept of the graph. Okay, we're going to look for any additional values. That could be like what we did yesterday with the maximum, minimum. It could just be some other ordered pairs, maybe like a table of values, because we want to try to make it fairly specific, kind of like whenever we're graphing, our goal is to make that graph as specific as we possibly can. So we're looking just for some additional values, some other ordered pairs that we can use to help us graph it and get a better idea of what it looks like. And then we're just going to make sure this all fits together, okay? And really what I'll tell you is, like, I know you can get a lot of this information right from your calculator. Okay, I'm going to show you how we can find some of that information with or without a calculator, but a lot of this information is going to be on the calculator. And so today when you do your assignment, it's going to be pretty calculator heavy. You can use your calculator to find a lot of these pieces of information. Okay, we only have 2 examples today. One of them is going to be in standard form, which we kind of saw yesterday, and then one of them is going to be in factored form. So I want to show you how to graph out of both. I want to show you how to find different things out of both. And that's really all we're doing today is graphing out of different types of polynomials. Okay, so the first example. 2x cubed plus x squared minus 8x minus 4. Okay, and once again, we talked about this yesterday. This is what we call the standard form of a polynomial. There's good and bad to each one. The bad with standard form is there's not a ton of information. I can just look at this equation and say, here's what I know about it. Okay, there's a few things that you can look at here and kind of determine, but a lot of the information is not just readily available here. Factored form is a lot better in that aspect. Okay, so if we go through the steps, I'm going to kind of walk through the steps here first, and then we're going to do the graph last. And I know some of you are probably going to be like, I'm just going to jump right to the graph. But I want you to show you where some of this information comes from, how it all fits together, and then put it into our calculator at the very end. Okay, yesterday we talked about the leading term test. And my leading term here is 2x cubed. Okay? And first of all, my degree is 3. So we know 3 is odd. We have to decide if it's even or odd. 3 is odd. My leading coefficient is 2, which is positive. That's the second piece of information we need to decide. And if you look back at your chart from yesterday, that tells us our graph is going to start down and it's going to end up. Okay? It just tells us our end behavior. So it's going to start down here and it's going to end up here. Kind of like the 3 that we just looked at a second ago. Hey, next thing that we're going to do is we're going to look for the zeros of the function. And we kind of talked about some of these processes yesterday. If I have 4 terms here, and I want to try to find the zeros of this function, then because we have 4 terms, we can't do like product and sum or slide and divide or anything like that. 4 terms is most of the time going to mean grouping, okay? And so we're going to write this out. We did a grouping problem yesterday. And I told you we're going to keep seeing them from time to time. So here's another one. 4 terms means 2 groups of 2. Out of the first group, what can I take out? X squared. And that leaves me 2x plus 1. Out of the second group, and remember our goal here when we do grouping, is I want both parentheses to end up to be the same thing, if we can. If we can't, then that means you can't group this. But out of these 2, I can take out a 4, but not only can I take a 4 out, I could actually take a negative 4 out. So always make sure that you take out the GCF. You might say, well, I could take out a 2 as well. We want the greatest number that we could take out, which would be 4, but because they're both negative here, we're going to actually take out a negative 4, and then watch what happens. Okay, and that may not always happen when you do grouping, and if these 2 are not the same when I do grouping, that means we can't factor it by grouping. And we'll talk about what that would look like later in the chapter. Okay, and then we said yesterday we're going to combine those together. X squared minus 4, 2x plus 1. And then x squared minus 4 is DOPS. So that would be x plus 2, x minus 2, and 2x plus 1. So if I wanted to find the x-intercepts, that's our goal here, find the zeros. Our zeros would be negative 2, positive 2, and then negative 1/2. Okay, and going back to what we talked about at the beginning, this is a cubic polynomial, right? It can have up to 3 x-intercepts, and sure enough, we have 3 x-intercepts. Doesn't mean you're guaranteed to have 3, but here we have 3. So those are the 3 places that this is going to cross the x-axis. So what I'm going to do here is I'm going to go ahead and start my graph. I'm going to start putting this information on here. Negative 2, positive 2, and negative 1/2. Those are the 3 places that this graph will cross or touch the x-axis. As we start getting information, we'll start putting that onto our graph. Okay, for step 3, we're going to plug 0 in for x. We're going to find the y-intercept. Because whenever I plug 0 in for x, it's going to be 0 something. And so that's going to end up somewhere on the y-axis. And here's the great thing about the y-intercept here. When I plug 0 in here, 0 cubed is 0 times 2 is 0. 0 squared is 0. 8 times 0, still 0, right? So 0 plus 0 minus 0, still 0. And so my y-intercept in standard form is always going to be the constant. It's always going to be the number at the very end of the function. And so my y-intercept here is going to be 0, negative 4. So we're going to go down 4 on the y-axis, and that's where it's going to cross the y-axis at. Okay. So you don't have to necessarily go and plug it in. You're just going to identify what that constant term is, and that is your y-intercept when it's in that form. Okay, we also said that this is going to have 3 zeros, 3 x-intercepts, and 2 turning points. That's kind of like what we were talking about earlier today. And if you wanted to, like, we could find some other points, and now is where we're going to put it into our calculator. And we're going to use our calculator to kind of help us sketch a path for this graph. We know that it's got to hit these points. We know that this needs to all kind of fit together, and so hopefully, like, when we graph it, with the information that I've found and the information that I graph it with is all going to kind of fit together. Okay? All right, so here we go. Let's put this into our calculator. And then all we're going to do is make a sketch. It's got to go through the x-axis at those 3 points. This is where it changes its direction. This is where it changes its direction. It's got to go through the y-intercept at negative 4. It's just got to make all of those things part of my graph. Okay? If you wanted to come up with some other points, you could, but typically those points will be enough to kind of help you guide the graph. Okay? And we definitely want to use those. We don't just want to slap up this graph and say, oh, here's what it looks like on my calculator. We want to use those points to kind of help us guide. Okay. Okay, questions on that one? Not too bad, right? Other than we had to do grouping on it. Wasn't too bad. Okay, and I think in most cases, standard form is the harder one to graph. It kind of depends on what the equation is and things like that. But the next one we're going to do is in factored form, and there's a lot of things about factored form that make this a lot easier. Okay, so let's do one with factored form. kind of saw some like this yesterday too. And we didn't really graph a whole lot yesterday. We did on a few just to kind of see what the graph would look like, but now we're kind of putting it all together. What we really did yesterday was we found what the zeros were. We found the x-intercepts. Because these are in factored form, we are not multiplying these together. We can find the zeros pretty easily, okay? But before I do that, this part's going to be a little bit harder, okay? If I ask you what the degree of this polynomial would be, what do you guys think? Be what? 4? Yeah. How come?
Could you add up all the degrees of each one?
Add up all the degrees. Absolutely, okay? Because this would be x plus 1 to the first. This would be x minus 2 squared, so we're squaring the x. And this is x minus 4 to the first. So 1, 2, and 1 means this one would have a degree of 4. In some cases, people will look at this and they'll be like, oh, well, 2 is the highest one here. But all of this is going to be multiplied together. There's no plus or minus signs in between the parentheses here. So this would be like one big polynomial. I'm not multiplying all that out, okay? Unless you have this burning desire to multiply all that out, we don't want to do that, right? That wouldn't be a whole lot of fun. And I'm not going to ask you to do that. The lead coefficient, if there's nothing in front of the x's here, I'm just going to multiply x times x squared times x, and that's just going to give me x squared. So my leading coefficient would just be a 1 here, because there's no numbers in front. So we have a degree of 4, which is even. We have a lead coefficient that's positive, and that tells us this graph is going to be up, kind of like a parabola that opens up, except it's a 4th degree, which means it's going to look a little different. Okay, my zeros. X plus 1 equals 0, x minus 2 equals 0, and x minus 4 equals 0. So that gives us x equals negative 1, x equals 2, and x equals 4. Okay, and here would be the other thing I would say would probably be beneficial for you to kind of decide, going back to what we did yesterday. This one has a multiplicity of 1 because the exponent on that factor is 1. This one has a multiplicity of 2 because my exponent is 2. And then same thing here. My exponent is 1, so this has a multiplicity of 1. And why is that important? Well, it's important because this one is going to go through the x-axis because we said yesterday if my degree is odd, then it's going to go through the x-axis at this point. But if my multiplicity is even, then it's going to bounce off the x-axis at 2. And then finally, it's going to go through at this point. Okay? So that really is just kind of telling you that the actions or what the graph will look like at those specific points. And so it'll be a little bit different than one we did just a second ago because it's going to hit the x-axis and bounce off of it, whichever direction it comes in from. Okay, this one's a little bit harder to find the y-intercept. You could probably do it off of the graph, but we could also do it pretty easily here. 0 plus 1 is 1. 0 minus 2 is negative 2, but if I square it, we become 4. 0 minus 4 is negative 4. So 1 times 4 times negative 4 would be negative 16. And that would be our y-intercept. 0, negative 16. Okay, once again, if we use the same information that we talked about just a second ago, this one's a little bit different because we said it has a degree of 4, but it's only going to touch the x-axis 3 times. So it will not touch it 4 times. Remember, we said it's not guaranteed to touch it 4 times. 4 is the most it could touch it, but it doesn't have to touch it 4 times. And the reason why it's not going to touch 4 times is because it has an even multiplicity at this point. And so that's going to count as kind of 2 of our zeros. It's kind of what we call a double root, where we count it twice. So one of the zeros counts twice. That's where we account for our 4 zeros at. Okay? And that's going to be something we want to be able to identify. Okay, so if we graph this, we know the zeros are -1, +2, and +4. The y-intercept is going to be all the way down here at -16. And then once we have those critical points, relative min and max would be something we would kind of find from our calculator anyway. I'm not asking you to do that a different way. Those would be the ones that we just really need to know how to find. Because eventually, some of these are going to be imaginary, and we need to know what the graph it tells us and what it means. So now we're going to go to our calculator. And all of this should fit together, hopefully. Things to kind of take place. So we're going to come down. We're going to turn. We're going to go up to 2. We're going to turn. We're going to come down again. We're going to turn one more time. And there's our graph. So really it is just a sketch, but it's a sketch with some critical points that we're using to help our sketch. Okay. X-intercepts, y-intercepts, minimum, maximum points are going to be points we definitely want to use. If you want to find some other points, all you have to do is go to your table, find some other points. If you feel like that would help you to graph it better, go for it. You would have a whole list of points you could list out here. I'm not going to necessarily do that here because I'm really more concerned about, can you find those really important pieces like the intercepts and the minimum maximum. And most of that should be enough to help us guide our graph. Okay. All right, that's it. 2 examples. There's a lot of stuff on each one, but a lot of stuff that we did yesterday too. All of these are talking about graphing in some